This is lecture 23 on evaporation and transpiration. We're going to talk about mainly today evaporation in this lecture, and I will touch on transpiration, which in most rainfall runoff models where we have to do continuous simulation, we combine the two terms together into one term called evapotranspiration. Within the evaporation modeling exercises, we're going to cover three types: the energy model, the aerodynamic model, and then the combined model. Evaporation is when water goes from a liquid to a gas phase, and this can occur in our context in hydrology, either from water bodies, saturated soils, or unsaturated surfaces. Evaporation is important in our hydrology problems, mainly in two contexts. First is water supply design, either in open canals or reservoirs, particularly in arid climates where evaporation it can be a major issue. You can lose several feet per year of water evaporated out of your reservoir in many of the arid parts of the world where it's very warm and the air is dry. We also have to concern ourselves with evaporation when we're talking about hydrologic simulation, when we're looking at continuous simulation models over the long term. For the most part, in CE234, we're going to be talking about storm event modeling, and so evaporation is not such a big issue because we're talking about a relatively short duration with a lot of rain or precipitation falling in a short amount of time, and we're worried about flood modeling. If we were worried about continuous simulation modeling, where we're not only worried about the flood periods or the periods where we had heavy rains, but also during the periods when it was dry or lack of rain, where we wanted to see what the response to the streams would be to the various times when you had dry weather versus the wet weather, we'd have to take into consideration evaporation. This is an example of a reservoir, and you can see where the water level has been. This is in Chile, South America. This is Puclaro Dam, where evaporation is large. This is a very arid part of Chile, and so right now they're in drought conditions, and you can see that the reservoir, not only through releases for water use for irrigation and other means, but also they've lost quite a bit to evaporation over time. There are several factors that impact evaporation, including the density of the water, something called the latent heat of vaporization, and the latent heat is the heat that's either absorbed or lost from a body or a thermodynamic system through no temperature change, but simply through a phase change. So in this case, we're talking about going from a liquid phase to a gas phase, being vaporization. So that would be the heat that was lost to the system due to this phase change. And then we have the big driver of net radiation flux, and that's basically from the sun. And that net radiation flux is basically the radiation absorbed minus the radiation emitted. And so we'll talk a little bit about that. The radiation absorbed is basically a product of the incident radiation that comes from the sun and that which is reflected, called the albedo, which is a term that many of you are familiar with. But you know, that's such things as reflection from clouds and other types of interferences with the radiation. And the emitted would be based on what the surface is, and the emissivity of the surface. You know, if it's a black surface, it's going to be less radiation emitted from it than a whiter surface, or you know, like snow cover. And those are products of temperature and the emissivity of the surface. That would be the influences, the driving forces determining the radiation emitted. We also have factors of sensible heat flux, ground heat flux, relative humidity, and wind velocity. And so we'll talk about these factors on evaporation as we develop the models for evaporation. A very simplistic way to look at and estimating the evaporation is through pan data, what we call a Class A evaporation pan is what you're seeing here in the photograph. And that's where we put water in a pan. You are measuring the airspeed here, and you are looking at how fast this water draws down in the pan, and that's the pan evaporation EP, and that would have units of length per time, so inches per day or millimeters per day. And then you'd have a pan coefficient, which would be determined experimentally, well, actually through numerical models, but you basically, because you have additional evaporation that would be due to losses of the surface here on the sides, your pan evaporation would be different than what you would actually have for an evaporation, say from a lake or a much larger body. So that's using the pan evaporation data. This is data that's the Texas Water Development Board has put out through some of their pan evaporation data they've collected. You can see this is starting date on this particular data set's 1954. It goes through present. I've clipped out just a small portion of that, and you can see that they're estimating as much as 63.91 inches in 1954. You can see how it's distributed through the months. You can see how that varies through years, some years less, some years, well, actually 63.91 looks like, well, yeah, that looks like the highest I see there, and just a quick scan of the annual column. But you can see during the summer months we have the greatest amount of evaporation in the July-August time frame, and during the winter months, as you would expect, we have less. The days are shorter, and the sun is not directly above, and so you're getting less radiation, so you get less evaporation. Let's talk about the evaporation by something called the energy method. So we've talked about the using pan evaporation data, which is as an empirical method to get at the evaporation. The energy method would be more of a theoretical method where we would measure particular parameters such as the radiation, incident radiation, what's the RI. We would have an estimate of the albedo, which would be the fraction of radiation reflected, the albedo, which is the alpha. And then we would have a measurement, as I said, of the RI, which is the incident radiation. And then the radiation emitted, the RE, would basically be calculated based on the emissivity of the surface, E, which we could have values for depending on what the surface was, whether it was bare earth, whether it was a lake, whether it was something that was soils with grass on top or something like that. We'd have the Stefan-Boltzmann constant, which is given here as 5.7 or 67 times 10 to the minus 8 watts meter squared Kelvin to the 4th power. So that's the temperature is measured in Kelvin, and this is the temperature of the surface in degrees Kelvin, which is your temperature in Celsius plus 273. And so if I look at this net radiation, which is the combination of these terms here that we've just discussed, that goes in the numerator of this evaporation by energy method, and in the denominator you've got the latent heat of vaporization, which is based on temperature. So that's the latent heat that the fluid water gives off based on just basically a phase change from the liquid to the gaseous phase, and this is the equation to compute that. And then this is the density of water, the rho W. And so putting those together would give us an evaporation rate, ER, by the energy method, and that would be in units of length per time, millimeters per day, or millimeters or meters per hour, or something like that. It all depend on to make sure that you had the right units here. This with your net radiation and your Stefan-Boltzmann constant, making sure that everything is dimensionally homogeneous. If we move over to another method, so the energy method is based on the radiation into the system and how the various, the water would lose its latent heat. If we're not concerned about that, another method would be, or if we don't have enough data to compute that method, we could look at the aerodynamic method, which basically looks at how the wind can move the moisture away from the surface. So if you have a lot of heat and you are able to vaporize the moisture off of, let's say, a lake, but you couldn't move the moisture, that saturated moisture above the, in the atmosphere, if you couldn't move that away from the lake would stop evaporating because basically everything above it saturated. So the aerodynamic method looks at how does the wind disperse that evaporated moisture, that moisture that's in the vapor form. And basically there's a lot of derivation that goes in behind this, but simply put, the evaporation by the aerodynamic method is equal to this constant B, which essentially is a vapor transfer coefficient, and this A sub S is the saturation vapor pressure, and the EA is the ambient vapor pressure in the air. So that's what would be occurring out in the atmosphere away from the area that's saturated. And you can calculate this saturation vapor pressure by this equation here, which is 611 times the exponential 7.27 times T, where the T is the temperature of the air system in Celsius, divided by 237.3 plus T. So that's your saturation vapor pressure. And then your ambient vapor pressure is just simply your relative humidity. It's a direct proportion to the relative humidity times the saturation vapor pressure. And so if you put these together, that is multiplied by B, which is the vapor transport coefficient, and that has units of millimeters per day per square meter. That's the evaporation by the aerodynamic method. This B here has the units of millimeters per day times pascals, so day pascals. And so if you look at this, we're going to be multiplying 0.00102 times the velocity of the air at a height Z2 above the water surface, and then I divide that by the log of the elevation that the velocity of the air was measured above the water surface, divided by ZO, which is a roughness height above the water surface, typically 0.01 to 0.06 centimeters as a typical roughness height when you're looking at air moving across a water surface. And so putting all these together, I can estimate the evaporation by the aerodynamic method. A combined method is used when you don't have essentially the energy supply is not limiting or the vapor transport is not limiting. You're going to use a combined method. When they're both are not limiting. You know, if you've got the energy a balance supply is limiting, you're going to use the energy method. When the air transport, the vapor transport is limiting, you're going to use the aerodynamic method. And so if we look at that, we can use the combined method. And here where you've got the evaporation by the energy method, that's ER. EA is the evaporation by the aerodynamic method. And you've got these weighting coefficients that are delta over delta plus gamma here, where these the gamma is the psychrometric constant, which is taken to be about 66.8 pascals per degree C, and the delta, which is the gradient of the saturation vapor pressure curve. And you can compute that by this equation here, where again this T alpha is air temperature, EA sub S is the saturation vapor pressure. And this is best applied over small areas where you've got detailed climatic data, including net radiation, air temperature, wind speed, humidity, and air pressure. When you don't have that, a simpler method introduced by Priestley and Taylor in 1972 for large areas discovered that EA was approximately 30% of ER. So they simply have this relationship boiled down to 1.3 times delta over delta plus gamma, which using the same coefficients are the same equation as before, 66.8 for the gamma, and this equation right here for the delta. And then essentially what you're doing is then applying the energy equation, the Rn, over the latent heat of vaporization, which is the LV, and then the density of the water, which is rho W. Again, this has been covered in a few earlier slides. So that's the Priestley and Taylor equation, and this is what's used in most of the mathematical models for continuous simulation, is this Priestley and Taylor equation. When we look at evapotranspiration, ET, basically over water, evaporation is all that occurs. But over ground, if you've got vegetation present, which happens in the growing season, we have transpiration as well. Now it's hard to separate out these two, and so most models lump them together and call it evapotranspiration to characterize both the evaporation and the transpiration together. And you have relative contributions of evaporation and transpiration to the ET, because that's going to vary through the year, obviously because of the growing season. In the January, February months, your transpiration is almost zero, and your evaporation is the main driver and is the majority of what ET would be. In the summertime, you're going to have the heavy growing season depending on where you're at. If you're in the desert Southwest, the transpiration is not so much, but if you're in the humid continental East, let's say you're in Mississippi or Alabama or even Missouri, your transpiration rate is going to be much higher during the summer months, during the growing season. There's numerous approaches to computing the evapotranspiration, but most of what I've seen is those that simply have Pan coefficients, and you multiply by Pan evaporation data. So before, when I talked about the Pan evaporation data, you had a Pan coefficient. You got the Pan evaporation data, but that's not really what the true evaporation will be over a lake, because it's a different system. It's a larger water body. So you had a Pan evaporation coefficients, or Pan coefficients that apply to that Pan evaporation data. So these would be Pan coefficients that would be altered to accommodate not only the evaporation of the bigger, large water body of the lake, but also the transpiration. And you can see those. This is an example given by I think this is actually in a textbook that you don't have that I use. But essentially, this is some research that was done in the late 70s, and you can see these Pan coefficients. If you've got your Class A Pan is surrounded by short green crop, and you've got medium relative humidity, you can see for light winds your Pan evaporation, your Pan coefficient is about 0.65. For your upwind fetch, a green crop, again, this is in meters. So if you've got short distances over your crop where your Pan is setting, that's going to be a different coefficient than if you had, let's say, 1,000 meters of fetch between where the green crop started and where your Pan was. And so you can get the idea of how to get these various Pan coefficients for predicting the evapotranspiration. Basically, many models simply apply corrections to the evaporation estimate to get the ET. As I've said, they'll use the Pan coefficients. We're not going to concern ourselves with that, because in this class we're going to be dealing mostly with flood hydrology on an event basis. The ET is minor consideration and can largely be ignored when we're doing the type of modeling and estimating that we're going to do in our CE234. But I did want to expose you to evapotranspiration and evaporation and the various models. That way, if you get into a situation where you have to do some continuous simulation modeling, or you're working on an engineering project involving reservoir water supply, and you have to allocate for evaporation off of that reservoir, at least you'll have some familiarity with the various methods used. That concludes this lecture.